Welcome. In this video, we will introduce our work, ReCLIP, Refined Contrastive Language Image Pre-training with Source-Free Adaptation. My name is Xuefeng. I'm currently a PhD candidate from the University of Southern California, advised by Professor Nevatia. This work was completed during my internship at Amazon, with collaboration with my mentor Ke and all the other amazing colleagues from the group. Here is the outline for today's talk. ReCLIP is a language image foundation model that matches image with their captions through contrastive training, which pull close the visual and text embedding from the same pair and push away embeddings from different pairs. With large-scale pre-training over 400 million pairs of wide-retrieved image caption pairs, ReCLIP has obtained impressive representation for both visual and text inputs and the ability to perform zero-shot classification. At the inference stage, ReCLIP generates adaptive classification weight from text embedding of the template-wrapped class names. Then, the category whose text embedding has the highest cosine similarity with the visual embedding of the test image will be selected as the prediction result. Although ReCLIP has demonstrated impressive zero-shot classification accuracy on diverse datasets, it has limitations. For example, on the Eurosat satellite images, ReCLIP achieves 98.2% linear evaluation accuracy with the frozen visual embeddings. As shown by the t-SNE plot on Eurosat images, ReCLIP generates discriminative visual embeddings that cluster well based on their categories. However, the zero-shot accuracy of ReCLIP is only 59.9%. One possible explanation is that the category names such as industrial buildings and permanent crop cannot effectively describe the difference of visual patterns from different cellular image categories. On the other hand, similar to all deep learning models, ReCLIP experiences degraded performance when the visual domain gap is too large. For example, on the patch camel dataset, ReCLIP has limited performance in generating discriminative visual embeddings for medical scan of tumor and normal tissues. Besides the gap in both text and visual domains, there are also misalignments between visual and text embeddings. As shown by the t-SNE plot of the ReCLIP visual and text embeddings on CIFAR10, the visual embeddings are clustered well, but the text embeddings are gathered together instead of locating at the center of each cluster. This phenomenon contradicts with the assumption of unified embedding space of ReCLIP, where text and visual embeddings from the same class should be close to each other. Therefore, we are motivated to build a source-free domain adaptation method to address these gaps and misalignments, enhancing the classification ability of ReCLIP without requiring additional labels. Specifically, in the source-free domain adaptation, we do not have access to neither labeled data from the target domain nor any data from the source domain. The only resource we have access are the pre-trained vision language model and unlabeled data from the target dataset, such as the test data. As shown by the toy example with statistic from CIFAR10, text embedding from the different classes have average similarity of 81%, while the visual text similarity from same class is only 22%. Our hypothesis of why visual and text embedding from the same class are far away from each other is that ReCLIP visual encoder is designed to convey rich information including background and texture. However, this information can sometimes be irrelevant to classification tasks, which creates the gap between visual and text embeddings. To remove such classification agnostic information, we construct a projection matrix P1 that consists of orthonormal basis of text embedding subspace by performing singular value decomposition. As shown by the statistic from CIFAR10, projection space P1 successfully pull close the visual and text embeddings from the same class. However, the text embeddings from different classes are still adjacent to each other, which makes the cluster from different classes are hard to be distinguished. A possible reason for the adjacent text embedding is the ReCLIP text embedding space is trained to represent vast number of concepts. However, templated class name might only require few dimensions to describe the difference of their text embeddings. Therefore, overlapped information and inactive dimensions has dominant the similarity calculation and makes them very close to each other. The good news is, during the singular value decomposition, the first axis of U, which corresponds to the largest singular value, describes the dimension where text embeddings overlaps the most. Therefore, by removing this particular dimension, we arrive at the projection matrix P2 that project everything onto the text embedding subspace while concentrating on their differences. As shown by the statistic from CIFAR 10, classes are almost perpendicular to each other after the projection. With an aligned visual text embedding space, we can then consider the text embedding from class names as labeled example and visual embedding from the images as unlabeled examples. By performing the label propagation algorithm, we obtain pseudo-labels for all unlabeled images. Overall, with unlabeled images and category names from a target dataset, we first create a visual and text embedding with clipped encoders, and then project them into the projected visual text embedding space. We employ two parallel components ReCLIP-T and ReCLIP-V to update the text and visual encoder separately. For ReCLIP-T, we update text encoder with the cross-entropy loss by comparing the pseudo-label with the cosine similarity between visual and text embeddings, in order to push text embedding closer to the visual embeddings based on the pseudo-label prediction. We only update the layer norm weights for efficient training. In ReCLIP-V, we update the visual encoder with cross-entropy loss by comparing the pseudo-label with cosine similarity between visual embeddings and their cluster centers, in order to push visual embedding close to each other based on the pseudo-label assignment. Since ReCLIP-T and ReCLIP-V optimize the model differently, they will diverge from each other, and the commonly agreed pseudo-label will have higher confidence to be accurate. At the end of each epoch, we perform label sharing and only updates the model on example where ReCLIP-T and ReCLIP-V agree with each other. To evaluate the effectiveness of ReCLIP, we compare ReCLIP with the state-of-the-art source-free adaptation methods AAD and PUF over 22 CLIP benchmarks. For all methods, we report performance from both peak performing epoch and the final epoch. For CLIP, we report both reported score from paper and our reproduced scores using single template prompts, as well as the multiple template aggregated prompts used in the original CLIP evaluation. As demonstrated in the table, ReCLIP provides consistent and significant improvement over CLIP, with 5% average improvement on final epochs and 6% average improvement on peak epochs over 22 datasets. In comparison of peak and final epoch, ReCLIP drops by less than 1% while AAD drops more than 25%, which demonstrates the effectiveness of label sharing strategy that stabilizes the noisy self-training. For comparison with PUF, since PUF is a prompt tuning based method, it has intrinsic limitation on the number of prompt templates and can only use the single template CLIP as base model for adaptation. ReCLIP, on the other hand, does not have such limitation and can leverage from the benefit of multiple template aggregation provided by CLIP, resulting in a much better overall performance. To have additional comparison with the official PUF results, we have also evaluated ReCLIP on the Office Home dataset. As shown by the table, ReCLIP can still obtain improvement over PUF even without the benefit of multiple template aggregation. In the ablation study on pseudo-label generation, we demonstrate that label propagation with our newly designed projection space P2 is shown to be the most effective and consistent way in generating accurate pseudo-labels. In ablation studies on label sharing, it is shown that the label sharing is effective in providing better results over ReCLIP-T, ReCLIP-V, and their simple average assembly. We have also demonstrated that ReCLIP is effective over various architectures such as ResNet50 and Visual Transformer B32, as well as different pre-training algorithms such as SLIP and DCLIP. We have made the ReCLIP code available online, and please scan the barcode or enter the URL to access if you are interested. Thank you.